Good evening, children. Good evening, Tanishka, Srijana, Netra, Danya. And good evening, Ashur. Good evening. Ananya. Madhumita. Good evening, children. Yeah. So we'll continue with volumes and surface areas. Yeah, so I think last class, the last sum we did was example 10, if I'm not wrong. Example 10 children on page 224. No, example 6. Yes.
Yes.
I think I also did question number 10 on page 217. Yes. Okay, we finished example 6. We finished example 6. Yeah, we'll have to continue from question number 10 on page 217. Yeah. Yeah, children. Question number 9. You have the book, NCERT? Williams. Children, question number 9. Exercise 13.2. Question number 9. All right. So in question number 9, find the lateral or curved surface area. Just a second. Yeah. So find the lateral or curved surface area of a closed cylindrical petrol tank. Closed cylindrical petrol tank. So closed meaning bottom, top covered, and it's cylindrical. All right. That is 4.2 meters in diameter and 4.5 meters high. So we are given a cylindrical petrol tank. Cylindrical petrol tank. It's a closed cylindrical petrol tank. All right. And the radius is, the diameter is 4.2. So the radius will be 4.2 by 2, 2.1 meters. And the height, 4.5 meters. Am I audible, children? Is my screen visible?
Yes, ma'am.
Yes, ma'am.
So it's a closed cylindrical petrol tank. Radius height given to us, but we have to find only the lateral surface area. Find the lateral surface area. All right. So how do you find? What's the formula? CSE of the tank. CSE of the tank is equal to 2 pi RH, correct? 2 into 22 by 7 into 2.1 into 4.5. Work this quickly. Yes, children, please work this and tell me the answer.
Ma'am, 59.40 meters per minute.
Correct. So it's 59.4 meters square. Yeah. So this is the answer to the first part of the question. The second subdivision now. How much steel was actually used if 1/12 of the steel actually used was wasted in making the tank? How much of steel was actually used if 1/12 of the steel actually used was wasted while making the tank? All right. So the steel actually used is the amount of steel you had purchased or that manufacturer had purchased from the market for building this tank. The steel actually used refers to the steel which the manufacturer or the person who's made the tank, so it refers to the amount of steel the person had purchased to build that tank. So how much he purchased is not the TSA. TSA is the amount of steel. Now I think it's a steel tank. What is it? Is it given? Yes, I think it's a steel tank. Yeah, how much of steel? Right. All right. So the TSA of the petrol tank, all right, the total surface area is the amount of steel present now in the tank. But that is definitely not what the maker had purchased from the market, because he purchased something and of that 1/12 was wasted. The remaining is equal to the TSA. What is the TSA of the tank now? So the maker had purchased some amount of steel from the market. How much he purchased, we don't know. We'll say X meter square. Okay, so the maker purchased X meter square of steel from the market. Now, in the process of building the tank or making the tank, 1/12 of what he purchased was wasted. So meaning 1/12 into X. 1/12 into X was wasted. Correct? He purchased X meter square. He purchased X meter square. And in the process of building the tank, 1/12 of what he had purchased was wasted. So what is now, how much of steel has gone into the tank? X minus X by 12, you can say. Okay, he had purchased X and X by 12 wasted. So this remaining, when you take the LCM, you get 11X by 12. This is the amount of steel present now in the tank. And what is this equal to? This is equal to the TSA. Just because we have found the CSA here doesn't mean that this is equal to the CSA. No. In the first subdivision, the question is to find the CSA. But where is the steel present in the tank? All over. It's all over the tank because it's a closed petrol tank. So this steel, 11x by 12, is equal to the TSA of the tank. Am I right, children?
Yes, ma'am. Yes, ma'am.
Sure? Madhavita?
Yes.
Yeah. So since we do not know how much was purchased, we'll say this is the answer to the first part. The second part now. Okay, so let the amount of steel purchased, let the amount of steel purchased be X meter square. X meter square. Wastage is equal to 1 by 12 of X. So that is X by 12 meter square. X by 12 meter square. I'll show you the slide, children. Let me just finish it. So amount of steel present in the tank. Amount of steel present in the tank. In the tank is equal to what he purchased, X minus wastage, X by 12, which is, on taking the LCM, 12X minus X, 11X by 12 meter square. This is the amount of steel present in the tank. And what is that amount of steel present in the tank? TSA. So clearly 11X by 12 is equal to the TSA of the tank. TSA of the tank. Now, how do you find the TSA? What's the formula? So 11X by 12 is equal to 2 pi R into R plus H. So substitute the values and find the value of X. And that is the amount of steel actually purchased. Work this, children.
Completed, ma'am.
Oh, yeah. Just a minute.
Yes, ma'am.
Yeah.
Completed, ma'am.
Yeah, what's the answer? What is the answer? So 11x by 12 is equal to 2 into 22 by 7 into what's the radius? 2.1. Okay, 2.1 open bracket r plus h, 2.1 plus 4.5. So 11x by 12 is equal to 2 into 22 into 0.3 because 7 ones are 7.3 times into, when you add this, you get 6.6. Oh, yeah, 6.6. Okay, so 11x by 12 is equal to, you can find the product, 44 into 0.3 into 6.6. 87.12, correct? 87.12. So x is equal to 87.12 into 12 by 11 into 12 by 11. X is equal to, come. So the amount of steel purchased, or the amount of steel actually used, is equal to 95.04 meters squared. Done, children?
Completed, ma'am. Completed, ma'am.
Okay. Arjun? Done. Srijana?
Completed.
All right. Okay. Yeah, question number 7. So we'll just talk about this answer again. So in this question, which we just worked, the radius was given to us. The height also was given to us. And it is a closed cylindrical tank. It's a closed cylindrical tank. It's a closed cylindrical tank. That means the material steel is used all over. The material steel is used all over. In the first part of the question, we were asked to find only the CSA, 2 pi RH. Though we know that the steel is used for the 2 circular portions also, the top and bottom. The question was to find the CSA, so we found the CSA. In the second part of the question, we have to find the amount of steel actually purchased. The amount of steel actually purchased, that we don't know. See, if there was no wastage, then the amount of steel actually purchased will be equal to the total surface area of the cylinder. If there was no wastage in the making process, then the total surface area of the cylinder will be equal to the amount of steel actually purchased from the market. But now, since 1/12 of it is wasted, we do not know how much the manufacturer purchased from the market. So let that be X. How much is wasted? 1/12 of this is wasted. So he's purchased X minus wastage is 1/12 of this. So X by 12. On taking LCM, we get 11X by 12. And now what does this 11X by 12 represent? This represents the TSA of the cylinder. Why? Because this amount of steel is now present in the cylinder. And where is it present? In the total surface area, all over. So TSA. That's why we equate 11X by 12 to the TSA of the cylinder. And find the value of X, which represents the amount of steel purchased by the maker. Same exercise, question number. No, these, yeah, question number 4. Question number 4. The diameter of a roller is 84 centimeters. Okay, roller, the diameter meaning it's a cylindrical roller. Diameter is given, that means there is something circular. All right. Question number 4. The diameter of a roller. So radius is 84 by 2, 42 centimeters. And its length, meaning the height, is 120 centimeters. It takes 500 complete revolutions to move once over to level a playground. Find the area of playground in meters square. So this is very simple for you. How many revolutions? 500 complete revolutions. How do you find the area of the playground? Area of the playground. So what of the roller comes in contact with the ground? Only the CSA. When a when a cylindrical roller moves over the ground, the curved surface area of the roller moves along the ground. Correct? The 2 circular ends, they don't come in contact with the ground. When you roll a cylinder on the ground, when you roll something cylindrical on the ground, only the CSA of the cylinder rolls over the ground or comes in contact with the ground. The circular ends, they don't. Correct? Or you can say, 1 second. CSA into number of revolutions. Right. 1 second. 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 1 Write down, children. I need to drink some water. Please write down. But I think you have to find the answer in meter square. Yes, children. So CSA into number of revolutions will be the area of the playground.
Completed, ma'am.
Yeah. All of you? Done, all of you?
Completed,
Yes,
ma'am.
ma'am.
Example 3. We'll not work it, we'll just understand what it is. So Savitri had to make a model of a cylindrical kaleidoscope for her science project. Okay. So Savitri had to make a model of a cylindrical kaleidoscope for her science model project. She wanted to use chart paper to make the curved surface area of the kaleidoscope. So it's given very clearly. She wanted to use chart paper to make what? To make the CSA of the kaleidoscope. It's given. What would be the area of the chart paper required by her? Radius and all that stuff is given. So it's given in the question that she's using, Savitri has to use chart paper to make the CSA of the kaleidoscope. So how much of chart paper would she need? CSA, which is 2 pi RH. And radius and height is given to you in the question. So that's a simple one. See, one end, from one end you'll have to see. So that is glass. The other end also, it should be visible, right? So the circular ends will not be covered with chart paper. If you've seen a kaleidoscope, the circular portions, the circular ends will not be covered with chart paper. Because from one end you look through the other end. So the chart paper will be used only to make the CSA of the kaleidoscope. It's something you see with from one end, you look through the other end. All right, and it's also given that she has to use chart paper to make the CSA, curved surface area of the kaleidoscope. So you have to find only the CSA there. Right? Yeah, exercise 13.1 is a test. It's because it has the very basic questions. I have nothing to say there. Similar questions. I'll not give you the same questions. So this is test in the next class, exercise 13.1, test in the next class. But same, meaning similar questions, which meaning different numbers. But exactly same versions, different numbers. Okay, so with this, we come to the end of volumes and surface areas. Our next chapter is circles. Circles, I'm jumping to the numerical ones where, you know, the circle with some details is given to you and you'll have to find the missing angle. All right, we are going to that now straight away. So I'll introduce all the theorems which we have in this chapter, and we'll straight away go to that part of circles, and then we'll come to the proofs. All right. So I need to give you the introduction regarding, tangent, secant, chord, minor sector, major sector, all that stuff. But that is not needed now for, doing the numerical ones. So we'll come to that later. Now let's see all the theorems in this chapter. Don't write anything. Okay. So now OM, you can see a circle with center O, circle with center O. AB is a chord, and OM is a line segment perpendicular to the chord AB. All right, we have a circle with center O. AB is a chord. OM is the perpendicular from the center to the chord. Now, what is the theorem? The perpendicular from the center to a chord bisects the chord. Bisects the chord. OM is a perpendicular from the center to the chord. So it bisects the chord, which means the result is that is what are we given, or what should be given. If you know that OM is perpendicular to AB, then the result is AM is equal to BM, or M is the midpoint of AB. M is the midpoint of AB. What should be known? OM. O is the center of the circle. So from the center, the perpendicular from the center to the chord, not from anywhere. The perpendicular from the center to the chord bisects the chord. So here we know that if you know that OM is perpendicular to AB, then you can conclude that M is the midpoint of AB. If you cannot assume both, you cannot say let OM be perpendicular so it bisects. If it is known that OM is perpendicular to AB, then the result is M is the midpoint of AB, or AM is equal to BM. Understand, children? Got it? Yeah, now write on this. Yeah, make a note of this, children. Not writing, you know what already is it.
Which one?
This one.
I
Done?
still take this down. Only this one I will write some screenshot.
Okay. Done, children?
Yes, ma'am.
Okay, see, some of us have learned it in school. So what you do, you take a screenshot of the introduction and you can complete it later if you want it. If you've already learned it from school and you have it, then maybe you would like to refer it from your school classwork. So what I'll do, you take a picture now. When we start working the numerical ones, from there you can write down. The introduction part, take a screenshot. If you want to write, take a screenshot, complete it later. Or if you already have it, you can just listen. Done?
Yes, ma'am.
Okay. So what we just saw is a theorem, not just a statement. The statement is a theorem. So now the next one, the converse of this theorem. All right. So the converse is, if you know that M is the midpoint, if you know that M is the midpoint of AB, then OM is perpendicular to AB. So it's just the reverse. If you know that AM is equal to BM, then the result is OM is perpendicular to AB. Just the opposite of the theorem. The line drawn from the center of a circle to bisect the chord. If you draw a line from the center of the circle to bisect the chord, then that line will be perpendicular to the chord. So from the center, if you draw OM such that M is the midpoint of AB, from the center O, if you draw the line or line segment OM such that M is the midpoint of AB, then OM is perpendicular to AB. Then OM is perpendicular to AB. If M is the midpoint of AB, then OM is perpendicular to AB. So circle, there's a chord AB, okay, center. Now from the center, you draw a line segment to meet AB at its midpoint, M. So now OM bisects AB. OM bisects AB. That means M is the midpoint of AB. In that case, OM will be perpendicular to AB. If M is the midpoint of AB, then OM is perpendicular to AB. Is that fine?
Yes, ma'am.
Yeah. So if you know that AM is equal to BM, then OM is perpendicular to AB. Done, children? The third one, equal chords. Equal chords are equidistant from the center. Equal chords are equidistant from the center. All right, so circle, center O, chord AB, and another chord CD. Okay, chord AB, chord CD. Now, when we say, when we have to, find the distance of a chord from the center, it's always the perpendicular distance. Distance is always perpendicular distance. So see here, from O, if you want to know, see, AB is a chord. AB is a chord. You want to know the distance of this chord AB from the center. What do you want to know? You want to know the distance of the chord AB from the center O. So for that, you'll have to draw the perpendicular from the center to the chord, because distance is always perpendicular distance. So see here. Oh, not W, M it is, sorry. All right, so what is OM? OM is, we draw OM perpendicular to AB. We draw OM perpendicular to AB. We draw OM perpendicular to AB. Why? Because distance is always perpendicular distance. Similarly, draw ON. ON perpendicular to CD. So now what is OM? OM is the perpendicular distance of the chord AB from the center. And ON, ON is the perpendicular distance of the chord CD from the center. Who can repeat this? What is OM? No, perpendicular distance of the chord AB from the center. What is OM, children? OM is the perpendicular distance, or simply distance. Distance is always perpendicular distance. OM is the perpendicular distance. OM is the perpendicular distance of chord AB, from the center. From the center. And what about ON? ON is the perpendicular distance. Perpendicular distance of chord CD from the center. Of chord CD from the center. So now, if you know that AB is equal to CD, then the result is OM is equal to ON. If the chords are equal chords, so if the chords are equal, if AB is equal to CD, if the chords are equal in length, then their distances from the center will always be equal, will also be equal. If two chords are equal in length, say AB is 8 centimeters, CD is also 8 centimeters. Chords AB and CD have the same length. Then their distances, that means their perpendicular distances from the center, will also be equal. So if AB given, meaning if AB is equal to CD, then OM is equal to ON. If AB is equal to CD, then OM is equal to ON. That's what is the statement. Equal chords are equidistant from the center. Got it, children? Particularly those who have not learned this chapter in school so far. Following?
Ma'am.
Yes, ma'am.
They skipped this chapter, ma'am.
Oh. But they're not doing this for you, is it?
Yes, ma'am.
What about quadrilaterals?
Yes, ma'am.
That they've completed.
Yes, ma'am, they have completed.
Oh my God, this is such an important chapter. Quadrilaterals can be omitted. This is an important chapter because we have circles next year also. And without the knowledge of the circles this year, how will we handle next year's circles? If they wanted to omit a chapter, they should have omitted the quadrilaterals. Anyways, it's very important, Netra, for 10th standard. So because your school has omitted the chapter, don't ignore it. Please learn. Yeah. So again, this is the converse. If OM is equal to ON, then AB is equal to CD. That is, what is OM? OM is the distance of chord AB from the center. What is ON? That's the distance of the chord CD from the center. So if the distance OM is equal to the distance ON, then the respective chords are equal. Then AB is equal to CD. If the distance of the two chords from the center are equal, then the chords are equal in length. Chords, look at the statement, chords that are equidistant from the center. Chords that are equidistant from the center are equal. So which means if OM is equal to ON, because OM is the distance of chord AB from the center and ON is the distance of chord CD from the center. So if the distances are equal, if OM is equal to ON, then AB is equal to CD. Is this fine?
Yes,
Take a
ma'am.
screenshot. Yeah. Are you taking pictures, children? Netra?
Yes, ma'am.
Yeah. So this is a very important theorem. Now, if I say AB is an arc, all of you understand arc AB? Arc AB. I've taken 2 points on the circumference of the circle. I've taken 2 points on the circumference of the circle with center O. And this is arc AB. Written like this, arc AB. Now we'll understand the angle subtended by arc AB at the center. Angle subtended by arc AB at the center. Okay, so for that, to make out the angle subtended by arc AB at the center, you need to join the ends of the arc to the center. See here, join A to O and join B to O. So what should you join? Join the ends of the arc. See, arc AB, right? Arc AB. A, B. This is arc AB. Here's the center O. So the angle subtended by this arc at the center will be join the ends of the arc to the center. Join the ends of the arc to the center. This is the angle. That is angle AOB. Angle AOB is the angle subtended by arc AB at the center. You need to understand this language. The, like circle language. Okay. Let me draw this again. Arc AB. Angle AOB is the angle subtended by arc AB at the center. Now let's take a point on the circumference of the circle. Any point, anywhere. Now supposing I take a point here and I call it C. All right. Anywhere on the circumference. Now this is the arc, right? This is the arc. I should not take the point here. I should not take the point C on this arc. On the remaining part of the circle. So that means circle. This is arc AB. Don't take C on this one. Don't take C on this. Take C anywhere here. Don't take C here on the arc. So arc AB, it makes angle AOB at the center. Take a point C on the remaining part of the circle. Now again join the ends of the arc AB to C. Join A to C. Join B to C. Now angle ACB is the angle subtended by arc AB at the point C on the remaining part of the circle. First, we take up an arc. Here it is arc AB. We join the ends of the arc to the center. We join A to O and B to O. And hence angle AOB is formed. And angle AOB is the angle subtended by arc AB at the center. Center O. Now take a point C on the remaining part of the circle. That is, don't take C on the arc itself. On the remaining part of the circle. And again join A to C and B to C. First you connected A to O and B to O. Now A to C and B to C. So now a new angle ACB is formed. Now angle ACB is the angle subtended by the same arc AB, but at a point C on the remaining part of the circle. Now there is a relation between these two angles. You can see from the name itself. You see here, angle AOB, angle ACB. See here, AB. Can you make out this AB? So the arc is AB. So this angle is at the center. This angle is on the circumference. Netra? Following because you have not learned it in school. Am I clear?
Yes, ma'am.
Yeah. See, from the name we can make out angle AOB and angle ACB. You can see here, AB, this is the arc. AB is the arc. And arc AB subtends an angle AOB at the center O. This is angle ACB at the circumference C. Now the relation is angle AOB is equal to twice angle ACB. That is, if this angle is 30 degrees, then this angle is 60 degrees. The angle at the center is more. If this angle is 30, if this is 30, this is 60. Is that fine? That's a relation between these two angles. Take a screenshot.
Ma'am.
Done?
Completing.
Yeah. Let's take another one. Circle, center O, arc AB, join A to O, B to O. Angle AOB is the angle. Tell me, is the angle subtended by arc AB at the center O, at the center O. Now let's take a point D here. Because you should not take on the arc itself. You should not take on the arc itself. So on the remaining part of the circle, say at D. Now join A to D and B to D. A to D and B to D. So you can see another angle here. Angle ADB. Tell me, is the
subtended by arc AB at the circumference at the point D on the circumference.
Yeah. Subtended by the same arc AB at the point D on the remaining part of the circle. On the remaining part of the circle. So the relationship is angle AOB is equal to twice angle ADB. Because both are made by the same arc AB. Both the angles are made by the same arc AB. One angle is formed at the center, the other is on the circumference. So the angle at the center is double the angle at the circumference. Take a screenshot, children. Done?
Yes, ma'am.
Yeah. All right. Now there's another. So this is one theorem. So the theorem goes like this. The angle. This is the theorem, children. I explained the theorem to you. Now this is the theorem. The statement. Okay. The angle subtended. The angle subtended by an arc at the center. At the center is double the angle. Is double the angle subtended by the same arc, subtended by the same arc at any point on the remaining part of the circle. On the remaining part of the circle. Why do we say remaining part of the circle? Because it should not be on the arc itself, as I told you. Now, this one is the arc AB. This one is the arc AB. This is the arc AB. The point, now this point D should not be on the arc itself. It should not be on the arc itself. So this is the remaining part of the circle. That point D can be anywhere on the remaining part of the circle. This is the remaining part of the circle, other than the arc. This is the theorem. The angle subtended by an arc at the center is double the angle subtended by the same arc at any point on the remaining part of the circle. Very important theorem. Yeah. Next, another theorem. Angle in a semicircle is a right angle. Angle in a semicircle. Angle in a semicircle is a right angle. Okay.
And can you previous slide, ma'am?
Sure, sure.
Yes, ma'am. Thank you.
Yeah. Yeah, so this is angle in a semicircle is a right angle. Circle, center O, diameter. Now again, take any point, take a point C, anywhere on the circle, take a point C. Suppose here. Join A to C, B to C. That is, you're joining the ends of the diameter to the point C. You're joining the ends of the diameter. AB is a diameter. Why? Because it passes through the center O. AB is the diameter because it passes through the center O. Now we take a point C on the circumference of the circle and we join A to C and B to C. And an angle is formed here. This angle is a right angle. Angle in a semicircle, because this is semicircle, right? See here, this is a semicircle. This is A, this is O, this is B, this is C, and yeah. Angle in a semicircle is a right angle. You can take a point here also. You can take a point D here, join A to D and B to D. You should join the ends of the diameter. A to D, B to D. An angle is formed. This is 90 degrees. Because this is also a semicircle. Angle in a semicircle is the right angle. See, this is not a right angle. Supposing circle, diameter AB, and you take a point C here. You join like this. This is not 90. The point should be on the circumference of the circle, not anywhere inside the circle. That point C or D should be on the circumference of the circle, not inside the circle or outside the circle. It should be on the circle. Angle in a semicircle is a right angle. For that, you should take a diameter, a point on the circumference, join the ends of the diameter to that point on the circumference. An angle will be formed. That angle is a right angle. Got it? Yes. Yeah. Another theorem. Angle in the same segment. Angles in the same segment of a circle are equal. Angles in the same segment of a circle are equal. So see here. Now I have to tell you what a segment is. Very simple also. Circle, chord. Now this part contains the center of the circle. This is called the major segment. I'll tell you why it's called a segment. And this is called the minor segment. This is called the minor segment. A segment is a region of a circle bounded by a chord and an arc. A segment is a region of a circle bounded by a chord and an arc. Chord and an arc. If you see a region like this in the circle, it's a segment. It's a segment. If the segment contains the center of the circle, if the segment contains the center of the circle, it's the major segment. If it has a center, it's the major segment. If it does not have the center, it's a minor segment. So see here, this one is the minor segment because the center is here. So this one is the major segment. What is the segment? It's a region bounded by a chord and an arc. So see here, circle, chord, PQ is a chord. So you can see here, chord and an arc. You can see an arc here. Minor segment. You can see the same chord and a bigger arc. You can see the same chord PQ and a bigger arc. This is the major segment. Major segment. This one is called the minor arc, and this one is called the major arc. This is called the minor arc, and this is called the major arc. Semicircle is exactly half, right? Semicircle. What is the length of the semicircle? Pi r. Like 2 pi r is the full length. 2 pi r is the full length. The length of a semicircle is pi r. The length of a semicircle is pi r. So a minor arc, the length of a minor arc will be less than the length of a semicircle. Because semicircle marks the, halves. So if the length of the arc is less than the length of the semicircle, it's a minor arc. If the length of the arc is more than the length of the semicircle, it's the major arc. So major, minor, you should compare with the semicircle, the length of the semicircle. Semicircle is only this one. This is a semicircle. So if there's an arc, so this arc, see here, like this arc is a minor arc because its length is less than the length of the semicircle. Now supposing the arc is here like this one, PQ. Now this one, PQ. This one is a major arc because the length is more than the length of the semicircle. Okay, so we were talking about the theorem. Angles in the same segment, angles in the same segment of a circle are equal. Okay, so circle. So segment means there should be a chord AB. This is the major segment. We'll do with the minor segment also. Now, in the major, in the major arc, take 2 points, P, Q. Okay, in the major arc, we take 2 points, P and Q. Now join A to P, B to P. Also join A to Q, B to Q. Now this angle is equal to this angle. Because they're in the same segment of the circle, both the angles are formed on the major arc. Both the angles are formed on the major arc, so they're equal. Angles in the same segment, because both the angles are in the major segment and they are formed on the major arc. Both the angles are formed on the major arc. Angles in the same segment of a circle are equal. So the measure of this angle will be the same as the measure of this angle. Similarly, if you take 2 points here, M and N, join A to M, B to M. The ends of the chord to M. Similarly, join A to N and B to N. So you can see 2 angles are formed. Those 2 angles will be equal. Same reason, angles in the same segment of a circle are equal because both the points M and N are on the minor arc. Both are on the minor arc. Both the angles are formed in the minor arc. So they're in the same segment, so they're equal. Fine? Got it, children?
Yes, ma'am.
Angles in the same segment of a circle are equal. Okay, now some properties of a cyclic quadrilateral. What is a cyclic quadrilateral? One second, children. Yeah, children, I'm back. So, what is a cyclic quadrilateral?
Opposite angles of cyclic quadrilateral add up to 180.
Yeah, so that's a property. That's a property. What is a cyclic quadrilateral? You're right, Danya, you're right. That's a property of a cyclic quadrilateral. My question is, what is a cyclic quadrilateral?
A quadrilateral formed by the chords of a circle.
By the chords of a circle. Okay. Okay. If the vertices of a quadrilateral, if the vertices of a quadrilateral lie on the circumference of a circle, the quadrilateral is a cyclic quadrilateral. So, yeah. So ABCD is a cyclic quadrilateral because its vertices lie on the circumference of a circle. See, it need not be like this also. You can just draw a figure like this. And if you say ABCD is a cyclic quadrilateral, then it means a circle can be drawn passing through the vertices A, B, C, and D. 1 minute. Let me start from here. If the vertices of a quadrilateral lie on the circumference of a circle, with a quadrilateral, how many vertices? 4 vertices. If all the 4 vertices of the quadrilateral lie on the circumference of a circle, then the quadrilateral is called a cyclic quadrilateral. So here, why is ABCD a cyclic quadrilateral? Because its vertices A, B, C, and D lie on the circle. But doesn't mean that a cyclic quadrilateral should always be shown like this. It can also be like this. If it is given that ABCD is a cyclic quadrilateral, then it shouldn't be like, where's the circle? The circle need not always be shown. Do not understand that a cyclic quadrilateral should always come with the circle. No. If I say, or if it is given that ABCD in this case, if it's given that ABCD is a cyclic quadrilateral, ABCD is a cyclic quadrilateral, that means you can draw a circle passing through the vertices A, B, C, and D. That means you can draw a circle passing through the vertices A, B, C, and D. Got it, children?
Yes, ma'am.
Yeah. The vertices are said to be concyclic. The vertices are said to be concyclic. So if the vertices of a quadrilateral lie on the circumference of the circle, it's called a cyclic quadrilateral. And the vertices are said to be concyclic. A, B, C, and D are said to be concyclic. Take a screenshot. Okay. Now the properties. Now properties of a cyclic quadrilateral. Properties of a cyclic quadrilateral. Opposite angles are supplementary. Opposite angles are supplementary. And also exterior angle is equal to exterior angle is equal to its interior opposite angle. Its interior opposite angle. So that means so if PQRS is a cyclic quadrilateral, then this angle plus this angle is equal to 180. And this angle plus this angle is equal to 180. Opposite angles are supplementary. The sum of these two angles is equal to 180 and the sum of these two angles is equal to 180. Also, in a cyclic quadrilateral, if you produce one side, supposing you produce a side RS, an exterior angle is formed. This exterior angle is equal to its interior opposite angle. So see, this is the exterior angle. Leave this angle, leave this one. This is the interior angle. Interior opposite angle, this one. So angle 1 is equal to angle 2. Angle 1 is equal to angle 2. 2 is the exterior angle and 1 is the interior opposite angle. See, this is the interior angle. For this exterior angle, this is the interior angle. Leave that. Interior opposite angle. Angle 2 is equal to angle 1. So when is an exterior angle formed? When a side is produced. When is an exterior angle formed? When a side is produced. So the side RS is produced. And you can see the exterior angle 2. 2 is equal to angle 1. Similarly, if this is produced, then angle 3 is formed. And angle 3 will be equal to angle 4. Correct?
Yes, ma'am.
Angle 3 will be equal to angle 4. All right. So I think with this, we are good to, start off with the numerical versions. Yeah. Now, from here, we'll start working, children. So I'll just tell you one more thing. You heard about the segment. Now we'll just see what a sector is also. What is a sector? So circle, circle. This region is called a sector. This region is called a sector. Now, why is this called a sector? Because it's a region bounded by 2 radii and 1 arc. See here? A region of a circle bounded by 2 radii and an arc is called a sector. The region of a circle bounded by 2 radii. See here? OA radius, OB radius, and AB is an arc. So the region of a circle bounded by 2 radii and an arc is called a sector. And this is the minor sector. The rest of it is the major sector. See, this is the rest of it. This is the rest of it. See, something like this. See, this is the minor sector, right? This one is the minor sector. The rest of the circle, take away the minor sector. Take away that. The rest of it is the major sector. See, it satisfies the definition. It's bounded by 2 radii, OA, OB, and an arc. See the arc here, and an arc. So this one is also a sector. This is a major sector. This one is a major sector. You can see it's bounded by 2 radii, OA radius, OB radius, and an arc, The region of a circle bounded by 2 radii and 1 arc is a sector. All right. So you heard what a segment is, and now this is a sector. All right. Yes, children, please take down the figure. Yeah, find X. Netra.
Ma'am,
Yeah, Netra, name the angle which measures 30 degrees. Name the angle.
ma'am, angle A.
Angle?
A.
Name the angle which measures 30 degrees. Yeah, somebody else?
BAC.
BAC, angle BAC. Angle BAC is equal to 30 degrees. Now, this is subtended by which arc, Netra? From the name of the angle, you can say. In the mid. Yeah.
Angle
The ends. The ends.
B.
Arc.
BC.
Arc BC. See here. Arc BC. Arc BC. And look at this. This is the arc BC, and this is the point A on the circumference. See here. B is connected to A, and C is connected to A. So angle BAC is made by arc BC at the point A on the circumference. Now, what can you say about angle BDC, Netra? Is that also made by the same arc BC? BDC.
Yes, ma'am.
But at a different point D on the circumference, right?
Yes, ma'am.
This is what is angles in the same segment of a circle are equal. You can see that both the angles are in the same segment. Both the angles are in the same segment. I'll show you how. See here. Circle. Please ignore the shape. Don't laugh, all of you. See here, like this it is. This is the major segment. This is the major segment. This is the minor segment. This is the major segment because this is the chord. This is the major segment. And see, both the angles are in the major segment, right? This angle is here and this angle is also here. Both are in the major segment. So they're equal. They're made by the same arc at two different points. Okay, so how do we present the answer and how do we find the value of X? All right. So first we start saying angle BAC is equal to angle BDC. Okay, reason angles in the same segment of a circle. Angles in the same segment of a circle, of the circle. You can just start with same segment, that's all. You don't have to write off the circle. Angles in the same segment are equal. So BAC is equal to BDC. Okay, so that means since BAC is 30 degrees, BDC, angle BDC is also 30 degrees. Now take up the triangle. In triangle BDC, the sum of the three angles is 180 degrees. So look at the triangle BDC. One angle is 70 degrees. There's another angle here, which is 30, which we just found. And X is the third angle, is equal to 180. So 100 plus X is equal to 180. X is equal to 80 degrees. In triangle BDC, use the angle sum property and find X, which is 80 degrees. Wasn't that simple, children? Understood? All of you? Got it?
Yes, ma'am.
Yeah. All of you write down this in your book. Done?
Yes, ma'am. Completed.
Yeah. Next figure. The heading is the same. Find x, okay? Yeah. Is AB the diameter, children? Class, is AB the diameter? Okay, yes, AB is the diameter because it passes through the center O. Is PQ the diameter?
Yes, ma'am. No, ma'am. Oh, ma'am. It does not pass through center O.
PQ is not the diameter. PQ does not pass through the center O. PQ is a chord. See, I've not marked this. I've taken a different point. This is O. The intersection is not O. The chord AB passes through the center O. So AB is a diameter. Chord PQ does not pass through O. So PQ is a chord. It's not a diameter. So whenever you have a diameter, you should think of the theorem, angle in a semicircle is a right angle. Angle in a semicircle is a right angle. See, a circle, diameter, supposing AB, diameter AB. So how do you use this theorem, angle in a semicircle is a right angle? Should take any point on the circumference. Suppose C, join A to C, B to C. This is 90 degrees. So see here, this is the diameter. This is the diameter, all right? AB is the diameter. And you can see the point P here. A to P, B to P. So isn't this 90 degrees? It's not given. We have to write that. Yes,
Yes,
or no?
ma'am.
I'll tell you again how that's 90. How do you identify angle in a semicircle? AB is the diameter. P is a point on the circumference. Join A to P, the ends of the diameter. A to P and B to P. So the angle, you can see the angle APB. APB, that is 90 degrees. Angle in a semicircle is a right angle. So that's what you should write first. Okay. So solution. AB, or you can say AOB is the diameter. Angle APB is equal to 90 degrees. Angle in a semicircle is a right angle. Angle in a, I'll just write SC, semicircle, okay, is a right angle. Is a RT angle, right angle. Now use angle sum property in triangle APB, children. In triangle APB, tell me.
90 plus 35 plus x is equal to 180 degrees.
Yeah, so we'll just call this as y, all right? We'll just call this as y. So 90, or you can even, 1 minute. You can even do this instead of calling it y. So angle, look at the chord, take the chord PB. PQB, PAB. See, from the name you can make out. I'll tell you, it's not at all difficult. Can you see the angles? Can you see the angles PAB and PQB? PAB. This is PAB. This is PQB. Both are made by the arc PB. One is at A, the other is at Q. See, at PB is the arc. This is the arc PB. Arc PB makes angle PAB here and PQB here. Angles in the same segment of a circle are equal. You can make out from the names of the angles. PB is the arc. PB is the arc. See here, PB is the arc. The arc PB makes angle PAB. The same arc PB makes angle PQB. You can go with the names itself. PB is the arc. A and Q, the points where the angles are formed on the circumference. So if this is X, this is also X, this is also X. All right. So angle AQ, sorry, not A, sorry. PQB. Angle PQB is equal to angle PAB. Why? Because angles in the same segment. Angles in the same segment of a circle are equal. Angles in the same segment are equal. So which means if PQB is X, PAB is also X. PAB is also X. Now use angle sum property. You have to find X, right? Now use angle sum property in the triangle PAB. So in triangle PAB, we wrote angle in a semicircle, right? So fine. So 90 plus 35 plus X is equal to 180. So 125 plus X is equal to 180. X is equal to 55 degrees. First, whenever in the figure there's a diameter, you should try to use angle in a semicircle as a right angle. Whenever there's a diameter, angle in a semicircle as a right angle will be used. So first do that. And then you can see in triangle PAB, you know two angles, 90 and 35. So you can find the third angle. And that third angle is only X. Done? Yeah. Done, class?
Yes, ma'am.
Yes, ma'am.
All right. What about the boys? Arjun, Srijana, Tanishka?
Completed, ma'am.
Okay. Srijana and Arjun? Arjun and Srijana, raise your hand. Both of you are not there. Next one. Find X. Yeah, children, those who have learned this in school, find X. Why Srijana and Arjun, you're not responding? Are you there, both of you?
The opposite angles equal only in a cyclic quadrilateral and unique quadrilateral.
No, only in a cyclic quadrilateral. Not equal, supplementary. Only in a cyclic quadrilateral, not any quadrilateral. Yes, Tanishka, Danya, and Madhumita, you've learned it in school. Expecting the answers from one of you, the correct answer from one of you, at least one of you.
65.
65. Let me see the figure. How 65?
Ma'am,
Can you
is
explain?
Ma'am, is it 115?
1,
115.
115. Okay, my subtraction was wrong. Yeah, correct. Yes, it is 115. I didn't subtract correctly, sorry. Yes, it is 115. All right. So, is AOCB a cyclic quadrilateral? Is Netra, is AOCB a cyclic quadrilateral? Okay. No, because A, B, C lie on the circle, but O does not lie on the circle. All the vertices should lie on the circle. But in AOCB, three vertices lie on the circle. The fourth vertex O does not lie on the circle. So it's not a cyclic quadrilateral. So you cannot use the property opposite angles are supplementary here because it is not a cyclic quadrilateral. Okay, so what you have to do is just take a point, take any point. Now, because this angle 130 degrees is made by this arc. This, see, that's very important, you know. This is the arc. This is the arc AC, which makes 130 degrees at the center. Yes or no, children? This is the arc AC, which makes 130 degrees at the center. Yes or no?
Yes, ma'am.
Yes,
Yeah.
ma'am.
So you need to take a point on the remaining part of the circle. Take a point on the remaining part of the circle. This is the remaining part of the circle. Take any point, anywhere. So supposing you call this as D. Join A to D and C to D. Okay. mark a point D on the major arc. Join AD and CD. Now, angle ADC is equal to, okay, you note this way, right? Angle AOC is equal to twice of angle ADC. AOC, ADC, both made by the same arc AC. See here, AOC made by arc AC at O. The same arc AC makes ADC at the point D. And it's a remaining part of the circle. It's not on itself. This is the remaining part of the circle. So a point D, join A to D, C to D. So this angle and this angle, they are related. The angle in the center is double the angle on the circumference. So 130 is equal to 2 times angle ADC. So angle ADC is equal to 130 by 2. 130 by 2, which is 65 degrees. Now you can use the property of a cyclic quadrilateral. Which is a cyclic quadrilateral now? ADCB. ADCB is a cyclic quadrilateral. So opposite angles are supplementary. We have another way of doing it. I'll tell you that also. So now you can see that this one, D, A, C, and B, this one. Okay. This is X. And this we just found is 65 degrees. Now, ABCD is a cyclic quadrilateral. Therefore, X plus 65 is equal to 180. Opposite angles are supplementary. Opposite angles are supplementary, correct? So X is equal to 180 minus 65, which is 115 degrees. We'll see an alternate solution. First, take down this. Done? Done, children?
Yes, ma'am.
Yeah.
Completed.
All right. So the alternate solution can be something like this. I'll let you go. So what you could do is you can find the reflex of this angle. All right. Angle AOC plus reflex of angle AOC is equal to 360 degrees. That is the sum of the angles around a point is 360. This is the angle AOC. This one is reflex of angle AOC. This is the angle AOC. This is called the reflex of angle AOC. So angle AOC plus the reflex of angle AOC will be equal to 360 degrees. Sum of the angles around a point is 360. So 130 plus reflex angle AOC is equal to 360. So reflex angle AOC is equal to 360 minus 130, which is 230 degrees. 230 degrees. So now let's draw the figure again. Okay, so this one is 230. All right, so this is 230. We just found that this is 230. Now see here, this angle is made by this arc. See, the angle and the arc, they'll go in the same ways. Meaning, see here, look at this one. This angle 130 degrees is made by this arc. If the angle is here, the arc will be below it like this. If the angle is like this, the arc will be here. If you mark the angle like this, its arc will be like this above it. If you mark the angle here, the arc will be below that. You can see it in these two figures. Here. How do you mark 130? This is 130, this one. Which arc subtends 130? See this arc below that. This arc AC makes AOC at the center. This is 230 degrees here. This is 230. 230 is subtended by, see, this is the angle. This angle is subtended by this arc at the point O. It's the same arc AC, but it's a major arc AC. See, in a circle, you know, when you take 2 points, if you refer to this arc, this is the minor arc AB. If you're talking about this arc, it's the major arc AB. This is the minor arc AB. This is the major arc AB. So this angle 230 degrees is subtended by this arc. AC only, but it's a major arc. So now, which is the remaining part of the circle? You should not take a point on this itself. So this is the remaining part of the circle. And on that we have B. The same arc AB, AC makes angle ABC on the remaining part of the circle. Listen again. Just shake your head and listen again. This is the arc that subtends this angle at the center. The arc is AC, it's the major arc AC. And the angle is angle AOC. It's called reflex of angle AOC. Is 230 degrees, which is made by arc AC at the center O. The same arc AC makes angle ABC. The same arc AC makes angle ABC. Because B should not be on the arc itself. B should not be on the same arc. It should be on the remaining part of the circle. And that's where it's B. It's on the remaining part of the circle. And see here, join the ends of the arc to B. Join the ends of the arc to B. A to B, C to B. So you have this angle X. So this angle and this angle are related. You can go by the direction itself. See here. This angle and this angle, they are related. How are they related? Reflex of angle AOC reflex of angle AOC is equal to twice angle ABC. So 230 degrees is equal to twice of X. ABC is X. So X is equal to 230 by 2, which is 115 degrees. I'll tell you again, please write down. I'll repeat it. So this is the alternate solution. I think Danya has done it like this, right?
Yes, ma'am.
Okay.
Done, ma'am.
Yeah. Done? Yeah. Done writing, children?
Completed.
Completed, ma'am.
Okay. See, it's very simple to remember. If that relation, no, this angle and this angle are related. AOB, ACB. See here, this angle at the center and above it, this angle. So angle AOB is twice angle ACB. Look at this figure. Okay. So this angle is made by this arc at the point O. I told you, if you mark the angle like this is the arc. This arc subtends this angle at the center. The same arc, take a point on the remaining part of the circle, not on this arc itself. The remaining part of the circle is this portion. So take a point C. Join the ends of the arc, A to C, B to C. So this is the angle. So this angle and this angle, see the same direction like this and this. So this angle and this angle, they are related. So reflex of angle AOB. Because when you say AOB, it is this angle. If you say AOB, it is this angle. You must say reflex of angle AOB is equal to angle ACB. I'm sorry, it's twice angle ACB. Reflex of angle AOB, this one. Reflex of angle AOB is twice angle ACB. Because that's what we have learned. Angle at the center is double the angle on the circumference. Angle formed at the center is double the angle formed on the circumference. All right, children?
Yes, ma'am.
So
Yes,
Netra, you must go through this before you come to the next class because the others have already learned it in school. So they might have found it easier to understand. I hope you also understood today's session. You go through the recording again if needed, or practice the sums from your book. Go through everything before you take up the next class. All right, Netra?
Yes, ma'am.
All right. All right, children. So that's it for today's session. Thank you so much. Good night.
Thank you, ma'am.
Thank you, ma'am.
Thank you. Good night.